this series, and in this video we are going to be talking about heating and cooling curves. And the way we're going to start this discussion is to talk about this lovely ice cube that I have here on the first page. And I want you to think about what really happens when an ice cube melts. When an ice cube melts, the heat that it is absorbing has to come from somewhere. Where does that heat come from? Well, the heat comes from the environment, the surroundings. Now, the surroundings could be your hand. If your hand is touching the ice cube, the heat can be coming from your hand and going into the ice cube. The heat can be coming from the air. The heat can be coming from the liquid that the ice cube is submerged in. Let's assume that that liquid is water. And when that ice cube starts to do its thing, it starts to heat up, it starts to melt, there is a specific series of events that takes place. And we're going to look at those graphically on the next slide. Okay? What happens to the ice cube when you put it in water? Let's say you have a glass of water and you put one ice cube in there. Well, the water cools off and the ice cube gets warmer or absorbs the heat from the water. But once that ice water gets to 0 degrees Celsius, it doesn't change temperatures anymore. If I were to take a thermometer and stick it in there, you would find that the temperature of the water remains the same. Why does that happen? Okay, all of these questions can be answered by looking at a heating curve. So we're going to get right to it, and let's look at the heating curve. Let me see if I can scroll down here. I don't know if I can. Let's see. Where's my scroller? Oh, there it is. Okay. Now, this might look familiar to you, as you might have seen it during your earth science class last year. And what I have up here is a typical, simple heating curve. And this heating curve is graphing temperature of the substance. In this case, we're going to be looking at water as our substance. Let's write that in. Pen, make it as small as you can. And the substance that we're going to be looking at is water. Maybe I should have written it up here so that it's out of our way. Let's write it up here. Oh, fiddle faddle. There we go. Water. H2O. Okay, so we're going to look at the temperature of this water as time goes by. And as time goes by, we're going to be adding heat to the substance. Where's the heat coming from? The heat is coming from the surroundings. And in this particular heating curve, we're going to assume that we're adding heat to the substance in a very regimented way. So let's say at 0 minutes, which is right here, right? We're going to start it at 0 minutes. At 0 minutes, and then we would have 1 minute, and then we'd have 2 minutes, and so on and so forth. Obviously, my graph is not perfect here, but you get the idea. So at every minute, let's say we're adding 100 units of heat. And the units of heat, because when we measure heat, we're going to be talking about joules. So for every minute that goes by, we're going to have 100 joules per minute being added. It's a very steady addition of heat. Okay, that way our graph comes out exactly the way that it's supposed to. Now, in the real world, that really doesn't happen, because you might put the ice cube next to the fireplace and it would be getting more heat per minute than if you left it on the table. But for all intents and purposes right now, we're going to be adding our heat at a very solid 100 joules per minute. Okay, let's talk about what happens. So let's say I have a solid block of ice, and the temperature is very, very low. It's below freezing. We're starting below freezing right here. Okay, and we start to add heat to that block of ice. Well, initially, we don't see anything happening visually. We don't see the ice doing anything. But in fact, the solid block of ice, as long as it is still solid, that block of ice is going to start heating up because we're adding heat to that block of ice. And see, my pen is slowly inching up, And then during this interval, we have a solid block of ice that is slowly, the temperature is rising. So at 1 minute, it got a little bit warmer. At 2 minutes, it got a little bit warmer. And then it gets to this point. Now we are still going to be adding heat at 100 joules per minute. But now we notice something very interesting happening. That solid block of ice starts to melt. Okay, it wasn't melting here. Nothing was happening visually. We couldn't see anything happening, except if we were taking the temperature, we would see that the temperature would be rising. But when we get to here, now we see a little bit of water accumulating around the block of ice. But if we were to be taking the temperature does not change here. Well, that's kind of interesting. I'm still adding heat because I'm at 2 minutes, and then by the time I get to 3 minutes, which would be somewhere around here, I have added another 100 joules of heat energy. Well, where did that heat energy go? The heat energy now is being used to melt the ice. The heat is going into or being stored in the water, the H2O solid becoming H2O liquid. Here, the heat was being used to increase the speed of the actual atoms or molecules of water. Okay, so we were increasing the speed of the molecules, follow my pen up, and then all of a sudden, now we got to this point, the molecules don't need to speed up any further because they are going to melt, but we're still adding heat, and that extra heat that's being added in there is going to be stored energy. So between this point right here and this point right here, the energy is still going in at 100 joules per minute, and that extra energy is being used to melt it. Now we get to this point. At this point, all of the solid ice is now liquid. And so this right here is liquid. And the liquids doesn't need to store any energy anymore, so the heat that I add between minute 5 and minute 6, 7, 8, I don't know, let's make it 9. Let's make it up to here, it's 9. Let's just say that. From here to here, that heat that I keep adding is going to increase the kinetic energy of those molecules. Remember, kinetic energy is the energy of motion. So I'm increasing the kinetic energy of those molecules. Okay, so we get to here. Now, they're moving as quickly as they can, and when they are moving as quickly as they can, I'm still adding heat. Well, that heat that I'm adding right there is now going to be stored in the molecules, and that stored energy is going to allow the water to boil, to change from a liquid to a gas. And then finally, when I get to here, okay, all of my molecules are gas, and the gas starts to rise in temperature again. And it will rise as I add my 100 joules for every minute. So 100 joules, now I'm up to here. So at these flat parts of the graph, let's erase this so it doesn't get too sloppy for us. At these flat parts of the graph, let's see if I can make this a little bit bigger. Right here and right here, there is no increase in temperature, but there is an increase in energy. Which kind of energy is being increased at those spots? Well, the energy that's being increased right there is the potential energy or the stored energy. I'm doing two things at once, so bear with me here. I'm trying to get my pen and talk to you at the same time. So right here on the plateau, right there and right there, we have an increase in potential energy. Now remember back from the last film or video, we talked about the word average kinetic energy, right? And I told you average kinetic energy is synonymous with another word. And that other word is temperature. Someday I'm going to get better at writing this stuff at the same time as talking to you. Okay, so average kinetic energy is the same as temperature. No, pen, don't die. Oh, it died on me. Okay, so we'll just say it. Average kinetic energy is temperature. Well, here's temperature, and temperature is rising on these slopes. It's getting higher and higher on the slopes. All three of these slopes. Okay? If the average kinetic energy is the same as temperature, and temperature is rising, then we can say that the average kinetic energy is rising. Should I ignore it or reopen it? Let's ignore it, and then I'll reopen it myself. Ignore. Okay, let's see what we get back here. So, they might ask you, at which interval is average kinetic energy rising? Well, average kinetic energy, right here, is kinetic energy rising. It's the same as temperature. So there's an increase in average kinetic energy. Again, I'm doing two things at once here. So here's an increase in kinetic energy. Increase in kinetic energy. Here's an increase in kinetic energy. And here's an increase in kinetic energy. KE is kinetic energy. On these flat parts, there is an increase in potential energy and an increase in potential energy. The way I like to remember this is, let's see if I can spell this correctly. Plateau, I think that's right. Potential energy. See the P here? P, and that is where phase change is taking place. Plateau, potential energy, phase change. And what I mean by phase change is I have, at this particular spot, I have a solid going to a liquid. It's a phase change. It's going from a solid to a liquid. And right here, I have a liquid going to a gas. A phase change. Okay? On the slopes, so these PPP right here, PPP, plateau, potential, phase change. On the slopes, it's not as neat and fun. Let's see if I can, hold on a second. Whoop, whoop. Okay, I'll get rid of that box for us. On the slopes here, we have an increase in kinetic energy or temperature. Okay? Alright, I'm going to erase this. Try to keep it neat. Everybody has all that information that they need. Now let's look at this little box that I have down here. Hopefully I can get it all on the same screen. Alright, let's label these as sections just so that we all have it. We have A, we have B, we have C, D, E, and F. Okay, in section A, B. Okay, right? Isn't that how you draw it in math? In section AB, what phase of matter do we have? We have a solid, so I'm going to put a little S there. Okay, is there a change in temperature? Sure, there's a change in temperature. Okay, yes, there's a change in temperature. Is there a change in kinetic energy? Yes, it increases the kinetic energy right there. Is there a change in potential energy? No, siree, bop. So as kinetic energy is increasing, potential energy is not increasing. Alright, let's do the next one. From B to C. From phase B, or interval BC. What phase of matter is it? Well, it is going from a solid to a liquid. So that's melting. Is there a temperature change? No. Is there a change in kinetic energy? No. Is there a change in potential energy? Yes, it's increasing the potential energy. is we're still adding heat. Remember we were adding 100 joules per minute? And we're still adding that heat, but there's no increasing temperature. So where did that heat go? Well, it's being stored. Sorry about that. Just moving my chair. Okay. Now, the next phase, we have C, D is our interval, and that is a liquid. The liquid is going, is there a change in temperature? Yes, there's a change in temperature. Is there a change in kinetic energy? Yes, it is increasing. There's an increase in kinetic energy. Is there a change in potential energy? No. If kinetic energy is changing, potential energy is not. Okay, interval DE. We are going from a liquid to a gas. And when we go from a liquid to a gas, is there a change in temperature? No, it's a phase change. Phase changes have no change in temperature. Okay, is there a change in kinetic energy? No, because kinetic energy and temperature are one and the same, right? So if I say kinetic energy, I'm really talking about temperature because I'm measuring the motion of the molecules. Is there a change in potential energy? Yes, sirree, Bob. We are increasing our potential energy. And then finally, EF. Okay, and what we have a gas there. Is there a change in temperature? Sure there is. Now that temperature can get really hot. That's why you can burn yourself much worse with steam than you do with boiling water, even though boiling water can do enough damage. Alright, so is there an increase in kinetic energy? If there's an increase in temperature, there is an increase in kinetic energy. And is there a change in potential energy? No. Okay? So that pretty much sums up heating curves. The only thing I didn't mention yet, let's make this bigger eraser. I want to just erase these so that they're not in my way. If we are talking about water in this case, let's say this was a heating curve for water. This first plateau right here will always translate to its melting point. So you can follow it over and you can see what the substance's melting point is. If this was water, which I'm saying it is, the melting point is going to be 0 degrees Celsius or 273 Kelvin. The boiling point, drawing my line all the way across here. Oh, my pen died again. So frustrating. Okay, the boiling point, just wait for that to come up again. Ignore that. Try to get it to come back. Come back! Come back! The boiling point, follow it over. I died again. Is going to be 100 degrees Celsius. 100 degrees Celsius. I'll have to find another way to draw on my desktop. There's gotta be another way. Gotta be, because this is crazy. Alright, so the boiling point, I'll make bigger dots, okay, is going to be 100 degrees Celsius. 100 degrees Celsius, or 373 Kelvin. And this one was 0 degrees Celsius, or 273 Kelvin. That's this right here. That point right there. Oh, my pen just died again. Okay, if you are graphing something on your own, and they ask you what the melting point is, it's always going to be this bottom plateau. If they ask you what the boiling point is, it's always going to be the top plateau. If they ask you what the freezing point is, freezing point is the same as the melting point. And the point of condensation is going to be the same as the boiling point. Okay? Alright, let's move on and see if I can get the pen to work for my next graph. Clear this off and let's examine this. Now in this particular graph, This is a cooling curve. And the only difference between this one and the other one is that we are now starting above our boiling point. We're starting way above. There's always two plateaus. The bottom plateau will be the freezing point and melting point. The top plateau is the boiling point and condensating point. It depends on which direction your graph is going. If the graph is sloping down to the right, like this one is, then it is going to be a cooling curve. There are times, and I should mention this right now while I'm thinking about it. Let's do red. That they might just give you this section of the graph. And if they do that, and this isn't there, let's say that's not there, they will tell you, this is a cooling curve starting above its boiling point. And so it says starting above its boiling point, well there's the boiling point, and I'm starting just above it. Clear that off. Or they will say, this is a cooling curve starting above its freezing point. And there's the freezing point, and it's starting just above the freezing point. If they wanted to, they could even do the same thing with the heating curves. They can, come here you, they can give you this section and say, this is a heating curve starting below its melting point. And here's the melting point, and so they're just giving you this section. Okay, they're not giving you the upper section. So whatever they say they're starting with, that's the first phase change that you're going to have. Alright, let's go back to the cooling curve for a second, and let's, oops. Okay, good, phew. I thought I lost it again. Alright, let's just fill this in real quick. I think I lost a line here. Oh, there it is on the next page. Okay, in interval AB, in section AB, okay, what phase of matter do we have? All the way up here. This is a gas. Okay, is there a change in temperature? Yes. Is there a change in kinetic energy? Well, if there's a change in temperature, there's a change in kinetic energy. So what's happening to the kinetic energy? It is decreasing in kinetic energy because the temperature is decreasing as time is going by. Is there a change in potential energy? Nope. If the kinetic energy is changing, the potential energy is not changing. Alright, section BC. It's a phase change. It's a plateau. Remember, P, P, P. Phase change, plateau, potential energy. So here's the plateau. And on the this plateau, I'm going from a gas to a liquid. Is there a change in temperature? Nope. What's happening to the potential, the kinetic energy? No change. And then what's happening to the potential energy? It's decreasing in potential energy. Decreasing. I should have just drawn an arrow going down. Okay, from C to D. We have a phase. What phase is it? Liquid. Change in temperature? Yes, sirree. There's a decrease in kinetic energy, and there's no change in potential energy because my kinetic energy is decreasing. Okay? It goes like this. If kinetic energy is increasing or decreasing, potential energy stays the same. If the potential energy is increasing or decreasing, and in this case it's decreasing because I'm in a cooling curve now, then my kinetic energy is staying the same. Alright, DE. I'm doing this mostly for the phases. In phase DE, or right here between these 2 points, we have liquid becoming a solid. Is there a change in temperature? No. Look, if I read a temperature here, here, or here, follow it across. It will always be the same temperature. There's no change in temperature, there's no change in kinetic energy, and my potential energy is decreasing. Alright, and I lost the next interval boxes on the next page, so we'll just do this. EF, we have a solid. Is there a change in temperature? Yeah. If I read it here, or here, or here, the temperature would be different. So if there's a change in temperature, then my There's a change in kinetic energy. Ooh, what happened there? Not a good eraser, but... Okay, there's a decrease in kinetic energy, and there's no change in potential energy. Okay, sounds good? Alright, if I said to you, what's the melting point? Or the freezing point? In this case, it would be freezing point because it's a cooling curve. The freezing point would be right here. Whatever that temperature is. And the melting point would be right here. Ooh, I'm sorry, boiling point would be right here, or condensating point because I am going in this direction. Okay, let me just make that clear because I misspoke for a second. Right here is the freezing point. Right here is the point of condensation. Okay? If it was a heating curve, if it was going up this direction, then this would also be the melting point, and it would be the freezing point and the melting point. And this one is the boiling point and the condensating point. Okay, depending on which direction you're reading. If the graph is cooling off, you're freezing. If the graph is warming up, you're melting. I hope that makes sense. Okay, let me clear this. Get a pen. And let's look at what kinds of things they might ask you. Oh, there it is. Take a look at that. Well, the kinetic energy is changing. Potential energy remains constant. And while potential energy is changing, kinetic energy remains constant. Okay, so let's do a problem, and then we're going to call it quits on this video. My videos seem to be about 30 minutes long, which is getting a little bit tiring for me because it's almost 11 o'clock at night, well past my bedtime. Okay, what happens if they give you, or if you're in lab and you get data that looks like this? They give you time 1 minute, what the temperature is, time 2 minutes, the temperature, and so on and so forth. Okay, we have to plot this data. Let's do it in green. It's kind of green right now. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so I'm going from time 1 minute to time 20 minutes. Okay, from 1 to 20. This is time. And we're going to be adding heat every minute. Okay, joules per minute. Maybe 5 joules per minute, maybe 100 joules per minute, maybe 1,000 joules per minute. Okay, and on this axis over here, we have temperature. And we're going to go from 15 degrees all the way up to 100 degrees. So I'm going to go by tens. Let me change colors. Okay, so we'll go 10 degrees, 20 degrees, 30, and they're Celsius, correct? Okay, 40 degrees, 50, 60, 70, 80, 90, and 100 degrees. And this is temperature in degrees Celsius. Okay, at time 1 minute, we have 15 degrees. Right there. At time 2 minutes, I have 23 degrees. At time 3 minutes, I have I'm going to go with 35. I think that's a 35. 35. At time 4 minutes, I have 39. And then I have 5 minutes, I have 39. 6 minutes, I have 39. And 7 minutes, I have 39. Then at time 8 minutes, it jumps up to 45. So 45. 9 minutes, it's 52. At 10 minutes, it's 59. At 11 minutes, it's 66. And then at 12 minutes, it's 66. And 13 minutes, it's 66. And 14 minutes, it's 66. Oh, look at that. Alright, 15 minutes, it's 75. 18 minutes, oh, I'm sorry, I'm at 16 minutes. 16 minutes, it's 80. And then 17 minutes, it's 87. And 18 minutes, it's 93. And then, 18 minutes is 93. And 19 minutes, it's 100. I told you, it's getting late. Okay, let's connect the dots. black. Across. Oh, this pen is really hard to draw straight lines with, so give me a little bit of credit here. That's really bad. You know what? Let's try it. Let's try that again. Okay, so I've got this, got this, got this. Oh, that's much better. Much better. Okay, now we have all of our data plotted. You are going to see data like this given to you in a problem. When you get data like this, there could be a little graph. If there isn't one, make one out of a piece of paper. Do what you have to do, okay? Now it says label all the phases of matter and points on the graph with the letters A through F. Okay, what color do you want? How about blue? Point A, point B, C, D, E, and F. Okay? And then it says label all the phases of matter. So this is a solid. This is solid going to liquid. That's a phase change. There's no temperature change at a phase change. Then there's liquid. Liquid going to gas. And gas. Okay, label all the phases of matter and points on the graph with the letters A through F. Okay, what is the melting point of the substance in terms of degrees Celsius? Just a little degree sign there. Okay. Alright, melting point. Well, melting is where it's going from a solid to a liquid, and that's right here. So this is my melting point. Read it across, and you get 39 degrees Celsius. That's not too hard, right? Okay, what is the freezing point in terms of degrees Celsius? Okay, if the melting point is 39 degrees Celsius, then the freezing point is also 39 degrees Celsius. Okay, this is melting because we are reading it in this direction. But if we were reading it in that direction, it would be the freezing point, liquid going to solid. So it is also 39 degrees Celsius. And that's the freezing point. I ran out of room here. Okay, what is the boiling point of the substance in terms of degrees Celsius? Boiling point is where we go from a liquid to a gas. This is the boiling point. And the boiling point is 66 degrees Celsius. Now if you notice, see there's no temperature change right here? And there was no temperature change right here? If I understood enough of this, I would understand that no temperature change down here is my first plateau, and no temperature change up here is my second plateau. So it's 66 degrees. Alright, what is the highest average kinetic energy of the substance in terms of degrees Celsius? Highest average kinetic energy. When you see the words average kinetic energy, you're going to replace it with the word temperature. Read it again. What is the highest temperature of the substance in terms of degrees Celsius? Highest temperature. 100 degrees. 100 degrees. Okay? Alright, I know you can't see the rest of these questions. During which intervals are kinetic energy rising? During which intervals are potential energy rising? Okay. Let's see if I can get it back on the line. It's not great, but okay. Potential energy is rising during intervals B and C. This is... what color have I not used? Oh, let's use green again. This is where potential energy is rising. It's the plateau, PPP, plateau, potential energy, phase change, plateau, potential energy, phase change. Kinetic energy is rising on the slopes. Right here, right here, and right here. Should have done it in a different color. This is kinetic energy rising because the temperature is rising. And temperature is another average kinetic energy is a fancy way of saying temperature. Okay? I know there was one more question, but I don't remember what it was. Let's see if we can just look. Oh, nope, that was it. Kinetic energy, potential energy, and where is the kinetic energy remaining constant? Well, the kinetic energy is remaining constant when the potential energy is changing, right? Potential energy is changing, so kinetic energy, which is temperature, remains constant on these plateaus. Alright, I hope you can now understand how to read these heating and cooling curves. And look over this video. If you need to watch it more than one time, do so. You will definitely have questions come up on a Regents and an exam on heating and cooling curves, and I hope this video helped you out.